Good afternoon, folks. How's everybody doing? Good to hear. Always a bit of a difficult question in Scandinavia. Everyone's like, is someone else going to shout? Shall I? I don't want to shout. What if I shout and I'm the only one who shouts? But that's all right, because we've got folks in here from all over the country, all over the continent, folks in from all over the world. And for some reason, a whole bunch of you had decided that what you want to do after your nice, generous lunch is to come and listen to a talk about algorithms. And now algorithms they're fascinating to me. Algorithms are the fundamental building blocks of computer science. And computer science is the bedrock that apps and websites and mobile and microservices, all this stuff is built on this layer of smart scientists doing interesting work to figure out how to solve certain kinds of problems. But this word algorithm, there are some people in here who probably you've encountered algorithms because you had to learn them at university to pass exams. And you learned them, and you're like, yeah, and then you went in, and maybe if you're the same sort of generation as me, you had to implement quicksort with a biro on a piece of paper to prove you knew how to program a computer. And then they gave you a degree, and you never did it again. Or maybe you've been cramming algorithms because, the job market out there is kind of tough, and some companies are like, well, we'll make them do quicksort on a whiteboard as part of the interview process. Or maybe you're cramming algorithms because you said you were going to talk about them at a conference, and then you're there looking them up the night before going, how does that one work again? But the idea for this talk came out of something I've seen happen many times. How many of you folks have done Advent of Code? Yeah. Advent of Code is great. It's a lot of fun, and every year it starts off kind of easy. It's a programming not even a competition, it's a set of puzzles. Every December, from December the 1st until Christmas Day. And there's always a real cute story about, Santa's elves, if they've got into trouble and a reindeer's stuck in a submarine, and you need to write programs to help kind of solve them. And day one is kind of easy, and day two is a little bit harder. And then on day four, you're looking at it, and you're like, the elves are lost in a maze, and the elves have to figure out how to get from down here to over there. And you try a couple of things, you can't quite figure it out. And so you ask for help. You go on Reddit, or you talk to one of your friends, or you go in a Slack chat, and you're like, hey, is any of you looking at that day 4? And someone's like, yeah, it's easy. You just use Dijkstra's algorithm. And you're like, okay, I wonder what that is. So you go in and you search, and you find Dijkstra's algorithm on Wikipedia. And it says, Dijkstra's algorithm is an algorithm for finding the shortest paths between nodes in a weighted graph, which may represent, and you're like, I don't have a weighted graph. I've got a maze with elves in it. Like, how is this thing going to help me solve the problem that they've got? Now, I'm probably being a little disingenuous here. The thing about pages like this, of course Wikipedia has to have an article about Dijkstra's algorithm. It's important. But to write good technical documentation, you need to know who your audience is. And Wikipedia is for everybody, which means the person who created and all the people who've contributed to this page, they don't know who their audience is. Like, are these mathematicians who want to study the time-space complexity of Dijkstra's algorithm? Is this like a high school student who's cramming because they have an exam in the morning? Is this me the day before my talk looking up how Dijkstra's algorithm works? And so they end up with this page which is kind of trying very hard to be accessible, but also the mathematicians are like, oh, we can express that using mathematical notation, and then people who can't read maths look at it and like, I don't belong here. It's been a horrible mistake. I'm not doing Advent of Code. And I think the biggest problem is that eventually, most algorithms, we are trying to take something that exists in a pure information space, and we are trying to communicate that from one human being to another human being so that the second human can eventually tell the computer how to do it. And so sometimes we fall back on, I wonder if I can just explain this in English. So, okay, we're going to start with 1, and we're going to count until we get to the limit, and then we're going to add the square of the number to the sum as we go along. And sometimes we're like, well, what if we do it in pseudocode? So it looks like code, but it's not code. It's like special code that's designed to be friendly, but computers don't understand. Number equals 1 and 1. Or maybe we're like, you know what? Let's just do it in real code. There you go, JavaScript. Everyone reads JavaScript, right? Or maybe we're going to write it in maths. And the people who can read maths are like, well, yeah, obviously you do that, because look how compact it is. And everybody else, hands up who can read the maths. Hands up who can't read the maths. Hands up who looks at that and you're like, what? But then eventually it clicks. And you go, I see what they get. I get it. I understand how it's going to work. And it clicks and this light bulb comes on in your brain. And then you go back to it and you're like, well, yeah, that's not how I would describe it. Like that's if I was telling someone in English, I wouldn't do it that way. That's not how I'd write the pseudocode. I definitely wouldn't do it in JavaScript. And still, if I could read maths, I wouldn't have had the problem in the first place, so that's not going to help. And so we have this thing that exists, this algorithmic set of steps and procedures, and the struggle is, how do we explain to people who haven't had the light bulb yet what is going on with that? Now, I said that the title of the talk is Algorithms Demystified, but actually I'm going to start off by going way in the other direction, because probably the best way to think about an algorithm is it is a magic spell. It is a thing. You folks have played D&D, right? And, like Baldur's Gate and Morrowind, it's the whole idea you can level up your character by learning something. And then once you've learned that spell, it becomes part of your spell book, and you can use that spell to go out and solve certain kinds of problems, and it changes the way that your character interacts with the world. Now, the other really important thing about algorithms is algorithms are these. They are the nuts and bolts of software engineering. How many of you folks do like you DIY in your house, like you put up shelves, or maybe you work on your bicycle or your boat or your motorcycle? How many of you make your own nuts and bolts? Like, how many of you own these? Yeah, a handful. But we don't do that, because if you've got to put up a shelf in your kitchen and the first thing you do is start making your own screws, you're an idiot. No. This stuff's important. It is really, I think, absolutely vital as a competent engineer to have at least some understanding of these little tiny components and how they work. But don't roll your own. Do not implement your own algorithms. Whatever language platform you're working with, it'll have code built into it already that will do things like sorting lists and searching arrays and all this kind of stuff. And that version will be better than your version because more people have looked at it and more people have optimized it and more people have helped find the bugs in it. So learn this stuff, enjoy it, play around with it, use it for Advent of Code, because that's the whole idea, is it's a lot of fun and you learn along the way. Please, nobody go back to work next week and implement your own sorting algorithm because, hey, Dylan said at NDC that we should do... Nah, don't do that. Don't do that. Now, this word algorithm comes from Arabic, actually from Farsi, ancient Persian, a guy called Al-Khwarizmi, who wrote a book in Arabic in the 9th century about how to solve certain kinds of problems using what were known at the time as the Hindu numbers, which was the kind of origin of the mathematics that eventually spread around the world. And that was translated from Arabic into Latin, where it became the Al-Khwarizmi method, and then Al-Khwarizmi became algorithm when it eventually got translated into English. And that word algorithm, it has a rigorous mathematical definition. It is a set of steps that you follow to reach a condition that says you have satisfactorily solved a particular problem. Now, language is a problem because we started out with algorithm in Arabic, meaning that dude. And then algorithm became a Latin word, meaning how you solve a problem. And then algorithm became an English word, meaning how you solve a problem. And then algorithm became an English word, being, yay, social media. The algorithm. The Facebook algorithm is not an algorithm. 1, algorithms are generally pretty simple. 2, algorithms are deterministic. 3, the job of an algorithm is not to show you 25 advertisements for a product you don't want, 3 advertisements for a product you bought yesterday, and a thing saying that your best friend is in town that would have been really cool if you'd known about it, except they already left last week. The Facebook algorithm, the Twitter algorithm, no, those things are not algorithms. The media has got hold of this word and started kind of twisting it. So yeah, that's not what we're going to talk about today. Now, let me introduce you to the most powerful algorithm in the history of computation. The universal algorithm can solve any problem. You start here at the beginning, and the first thing you do is you say, are we done? And if you're done, woo, finished, excellent, brilliant. And if you're not done, you do stuff. And then you go back and you check, are we done? Now, there is another concept which comes up fairly early on when you start exploring this stuff. This is the one that breaks people's brains. I studied computer science at a university in Southampton, graduated in 2000, so it's kind of September 97, which is quite a long time ago. And it's this class of about 100 undergraduates, all of whom are there because they like computers. And they've gone, yeah, I like computers, I'm going to do computer science. And day one, they're like, this isn't how I remember this stuff working. And, there was a sort of gradual attrition process over the first couple of weeks. There's lots of people who really enjoyed playing games and hanging out on bulletin boards realized computer science was not for them. And the week with the greatest attrition rate was the week that we learned about recursion. Because recursion is what happens when do stuff is, well, we're going to run the universal algorithm. Except inside there, we're going to run the universal algorithm. And inside there, we're going to run the universal algorithm. And the thing about recursion as a concept is it's like building a stone archway. Like, it either works or it doesn't. There are no intermediate steps where you can be like, okay, the recursion is almost working. Because either it does nothing, or you have an infinite loop, or you've got it right. And there's very little kind of, forgiving learning curve between these three steps. Now, a great example of a recursive algorithm. Recursion is all about, you need two things. One is you need an exit case. You need to know, when are you finished? So let's do I've tried to keep this talk from having any code in it, because algorithms aren't about code. Code is just the best thing we got to make them happen. Algorithms are conceptual. So let's build a tower, and we got to build a tower that is height h, and so the algorithm for this is h is 0, you're done. Everybody in the room, build me a 0 height tower. Well done. Excellent, you're all promoted, fantastic job. If h is not 0, what you're going to do is you're going to put down a block, and then you're going to build a tower on it, whose height is h minus 1. So let's build a tower height 4. First we put down a block. And then, okay, are we done? No, we're not. Okay, now we build a tower of height 3. So we put down a block. And then we build a tower of height 2, which means we put down a block, and we build a tower that has height 1, and we put down a block, and now we build a tower which has height 0, and, well, we know how to build a tower of height 0. We've already done it. And so we're finished. And so this is the idea of recursion, is a way of, now you'll find recursion applied in two different ways. One is you'll take a big problem, you'll nibble a little piece off the end, and you'll recursively solve the rest. And the other way is you'll take a big problem, and you'll crack it in half, and you'll recursively solve each half by cracking them in half and cracking them in half, and then you'll kind of put the whole thing back together and up with a solution at the end. And this is why it melts people's brains, is because they're like, no, you can't just keep calling yourself and yourself and yourself. And this is what happens if you don't get the exit clause right. Now, there is another kind of difficulty with implementing. I'm actually going to step that back just so that we don't end up 87 levels deep in Winnie the Pooh. One of the other things about algorithms is having confidence in them, because was any of you here last year? Because last year we had a guy called Matt Parker doing stand-up maths at the party, and he told a story about writing an algorithm in Python to solve Wordle that was going to run for 31 days. So he started it going, and he went to Australia for a month. And when he came back, it had got a result. And then he put it on the internet, and people on the internet started optimizing it, and someone got it down to 6 milliseconds. So, but, one of the challenges with this, particularly with things like Advent of Code, is you'll start the program running, and after 10, 15, 20 seconds, it's just sitting in a loop. And if you're confident that you've got all the cases right, maybe you just need to leave it running for a few minutes. Or maybe you got it wrong, and it's just spinning and spinning and spinning. And so this is where understanding the escape clause in recursion becomes important. All right. Let's look at examples of why algorithms are important. So we're gonna play a game of Scrabble now, and we're gonna play a game of Scrabble against a millennial because we enjoy a challenge. We like watching language evolve, and we're there putting our Scrabble tiles on the board, and our opponent plays the word yeet, and we're like, yeet is not a word, and I say, yeah, it's a word, and you're like, go on then, use the word yeet in a sentence. And they say something, yeah, it's like when you eat the roadman because the OG drip's got no riz, no cap, ohio, skibbity. And you're like, no, none of these things are words that exist in the English language. All right, let's check the dictionary. Because Scrabble says if you challenge a word, you got to look it up in the dictionary. Now, we got our Scrabble dictionary from the Pirate Bay because we're cheap. And so what we've got is we got a list of words. Is yeet in the list? Now, I kind of clocked myself. I reckon I can check 4 or 5 words a second with a reasonable degree of accuracy. So for me to check our Scrabble dictionary for the word yeet is going to take me 2 or 3 minutes. And if our opponent keeps playing words that we don't think are words, this is going to be a very, very slow, boring game of Scrabble. Now, we might get lucky. We might find yeet as the first word on the list. Oh, yeah, we found it. All right, fine. You're allowed to play the word. Or we might have to check the step. No, beer, no. Unit, wash, move. No. Now, this is the problem. This list is not in any order. So what we're going to do, we're going to go back to Pirate Bay. We're going to find a better Scrabble dictionary. And our next move, our opponent is going to play Riz. And first of all, where did you get 2 Zs from? There's not 2 Zs in a game of Scrabble, but they're like, no, it's millennial Scrabble. It's okay, whatever, extra letters. So let's go and look up Riz. Now we've got a dictionary that is sorted. Our dictionary is in, now I realize that we are in Denmark right now, where they have a slightly different alphabet to Sweden, who have a slightly different alphabet to Finland, who have a very different alphabet to the UK, and people all over the world, they have their own alphabets in their own alphabetical order. This is the English-Latin dictionary alphabetical order, case-insensitive, accent-insensitive, just in case that's a problem for anybody. And so what we're going to do is, if the list is empty, it doesn't matter. There are no words in an empty dictionary. All Scrabble moves are illegal. Otherwise, we look at the middle of the list. And it's easy to find the middle because it's in order. So we'll point at that one. Is that word the word we want? Is lion Riz? No, it is not. If the word Riz is in our dictionary, is it going to be before or after lion? After, yeah. Okay, so we throw away the first half of the dictionary. Right, now we look at the middle of what we got left. Self. Is Riz self? No. Is it before or after? Before. So we throw away the second half. Pick. Before or after? After? Before or after? Yep. And each time we do this, we are reducing the size of the problem by half until eventually we get down to a very, very small dictionary indeed. And we're like, well, there's one word left. Is that word Riz? No, it is not. So one, we are confident that Riz did not occur in our Scrabble dictionary. But two, if we want to insert Riz in the next edition, we know where to put it because we found the position in that list where that word was going to go. Now, I sort of magically I said, yeah, we just went on Pirate Bay and found an alphabetical dictionary. That's not actually how it works. Because sorting, the ability to take a bunch of elements in a list and put them in some kind of defined order, this is taking messy, chaotic data from reality and making it all nice and neat and well organized so that we can go in and we can find the things that we need. And to implement sorting algorithms, there are two things we need to think about. One is we need a rigorous definition of alphabetical order or sort order. We just need a way of saying if you've got two pieces of data, you can decide which one goes first. Now, it doesn't matter how you do that. The important thing is that you've got to use the same rule for sorting the dictionary as you use for searching the dictionary. Otherwise, you're never going to find things which are actually in there. Now, the other one that you've got to consider is something called space complexity, storage. Any of you folks, you ever reorganize your bookshelves at home? Now, the nicest way to reorganize a bookshelf is you get another bookshelf, which is the same size, and you take a book off the first shelf, and you're like, that one will go there, and that one will go there, and that one, and that's nice and it's neat. Most of us do not have enough space to have an entire spare bookshelf, because as soon as you get a bookshelf, you're like, I can buy more books now. And so the way you do it, now, when it comes to sorting books, you take a book off, and then you have to try and make a gap for where it's going to go. Or you take all the books off the bookshelf, and you pile them up on the floor, and pile them up on the bed, and pile them up on the stairs, and then your friend says, hey, you want to come for a drink? And you go for a drink, and 3 weeks later, there are still books piled all up and down the stairs because you're in the middle of sorting them out. Space complexity is about, do you have enough room in your computer to make a copy of your data and sort it somewhere else, or do you have to do it in place? Do you have to sort it where it exists? Now, let's look at some examples. We're going to kick off with one of the nicest, friendliest sorting algorithms. We're going to play a game of bubble sort. Now, I am going to need 10 volunteers from our studio audience. Now, if you would like to volunteer, you will not be individually humiliated, but the whole thing as a whole might be entertaining. Also, you might end up with pictures of you on the internet because we've got photographers hanging around and stuff. So I need 10 people who are up for that. 1, 2, 3, 4, 5, 6. Come on. 7. 8, 9, 10. Fantastic. Now, what I want you to do, 8 of you stand down here. So you're going to stand across the front of the stage. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. All right, so you in the NDC crew t-shirt, you're going to come up here. You have a very important job to do. You are going to be the flag officer. So I'm going to give you this. In a moment, you're going to get the rules. And you on the far end, you come up here. You also have a separate job to do. So your job in this is you are going to be what we call the looper. You are going to need your special sunglasses for this role. Now let us introduce the rules of bubble sort. So these are the elements, all of you down the front. Now when we did this in Norway a few months ago, the elements couldn't see the screen, which made it very entertaining indeed. So we fixed that for this one. So when somebody shouts go, you check if you are wearing a helmet. If you are wearing a helmet, you look at the person on your left. If you're taller than them, you are going to swap places. Otherwise, you give them the helmet. You understand the rule? If you're not wearing a helmet, you don't do anything. So we are going to start the algorithm off over here. So there you go. You're going to get the helmet. Now let me introduce the other element. The flag officer, at the start of the game, you lower the flag. If you see two elements swap places, you raise the flag and keep it raised. And the looper, your job is watch the helmet. If the helmet wearer sits down, you take the helmet and you move it back to the beginning of the list. You good? Is everybody comfortable with the algorithm as currently implemented? All right. Go. Go. Now, we've introduced a very interesting case here. Sort algorithms are what is known as stable or unstable. A stable algorithm, if two things are equal, they will be in the same order when we get to the end of the operation. If an unstable algorithm is running, it means two things that are the same might get switched or they might get not. So what do we do? Are we going to run stable or unstable? Unstable. Unstable. Let's run unstable. Right, so you two swap places. All right. Go. Flag officer up. Yep. Swap places. Good. Go. 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 Oh, hang on. We got an edge case here because there was no one on your left. So if nobody is standing on your left, when I shout go, you sit down. Go. 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 Is there anyone standing on your left? Sit down. Go. 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 Anyone standing on your left? Now, the reason the algorithm is called bubble sort is you'll notice when one of the taller people in the group reaches a certain point, they just kind of bubble all the way up to the top. So go, 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 go. Mind you don't sit on the speaker. Go. Go, 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 go. Should we overclock it? Go, 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 go. And eventually, if somebody wearing a helmet sits down, you look at the flag. Now, if the flag is already up, you lower it, but if the flag is already down, you shout the word sorted. Yeah. So what we've implemented there is we've implemented bubble sort. Now, what we're going to do now is with that extra rule in place, we're going to run the algorithm again. So all of you stay where you are, but all of you stand up again. Okay. So at the start of the game, lower the flag. The flag is down. If you see two elements swap places, raise the flag. You ready? Elements, go. Sorted. Oh, no, you got to, we're not quite there yet, because we got to do one pass through the list. So if you say go, is the person on your left taller? So give them the helmet. Go. 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 And at this point, the flag is still down. Sorted. Sorted. Let's give a massive hand to our data set. Thank you, folks. You may all go and sit down. By the way, they assured me this is a 100% authentic Danish historical Viking helmet. So, and I'm sure the guy in the tourist souvenir shop has a PhD in history, so that's fine, right? The props will be making a return tonight at the PowerPoint karaoke at the party, so look out for that. So that's bubble sort. And the whole point about bubble sort, it is not the best, it's not the fastest, but it is the friendliest. It's relatively easy to understand, and as you can see, as soon as somebody relatively tall gets the helmet, they just then swap, 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 and they bubble to the right position in the end of the list. And then the last thing we did there is we introduced this edge case, where if the list is already in order. Now, this is one of the weird edge cases for sorting algorithms, is some of them work very well unless you give them a list which is almost in order, in which case the whole thing completely falls apart. Now, we are not going to visualize sorting algorithms with volunteers because the chaos would be unbounded. We're going to visualize them like this. Now, it's a rite of passage. There's a lot of folks out there on the internet who've used sorting algorithms as a way to build little visualizers. It is astonishing how many of them get the visualization right and get the algorithms wrong. If you are going on like YouTube and you're digging around and searching for examples of this, I found quite a lot of these where it looks beautiful and it's got, you'll see in a second, animation, sound effects, but they've actually screwed up the sort underneath it. This one did not. This one is up on GitHub. It was built by somebody whose name is at the bottom of the slide, but my eyesight is not that good. Mazzuli, I think they are. You can find the links to this in the video afterwards. This is bubble sort. Now, this is where somebody on the other side of the curtain is like, are they playing games? And comes running and says, oh, I thought it was Space Invaders. Now, let's start talking about another really important characteristic of algorithms. Some of you folks, if you've studied computer science or you worked with people who do, will have come across Big O. And you can tell it's Big O because I've included a banana for scale, so you can see how big the O is. Big O is mathematical notation for, now, at a sort of very superficial level, it's how fast is the algorithm, but actually it's more complicated than that. So let's run another example with the rest of the group here. What I want you to do is I'm going to show you a list of data. I want you to find the first word in the list. You ready? Go. Yeah. So you're going to say it, otherwise we don't know. We infinite loop, waiting for the exit condition. All right, you ready for the next one? Go. Yeah, easy, right? Trivial. Now this is big O of 1. Linear, constant time, not linear, it's constant time. It doesn't matter how big the list is, because in computing, we almost always know where the beginning of the list is. And if we're looking for the first element, or like, just give me the first 5 numbers from that sequence, doesn't matter how big the sequence is, big O of 1 is constant time. Same amount of time to process, doesn't matter how big the input gets. Okay. Next question, I'm going to show you a list. I want to know, does the list contain the word drip? So, first, no. No? I was going to check my phone for a second. Now, I don't actually know whether it's in there or not. I didn't check. At this point, to know whether that list contains the word, because the list is not in order, you need to look at every single element. No. Now, if you do find it, you might bail out early. You might like, yeah, we found it relatively quickly. But to be confident that the list does not contain the search term, you need to check every element, which means you need to run one comparison for everything in the list. This is what's called linear time. If the list gets twice as big, the algorithm takes twice as long. If the list is 10 times as big, the algorithm takes 10 times as long. All right, I want to know if the list contains any duplicates. Does the same word appear in the list twice? No? Yes? File. Very good, yeah, we have a duplicate. Now, the only way to do this one is we're like, okay, well, it's not in any kind of order, so what we've got to do, we've got to look at byte. And then we've got to check the rest of the list to see if any of those words are byte. No, they are not. We have to look at horn. Now, we don't need to check byte, because we've already checked that byte is not horn, so we don't need to check that horn is not byte. So we've got to compare horn to all the rest of them. No, it's not a duplicate. We've got to compare that, run that across the whole list. That is not a duplicate. What this means is that if there's 360 elements in the list, byte, we have to run 359 comparisons. Horn, we have to run 358. That, 357. Flag, 356. People who've done mathematics and number theory are like, I know this one. These are triangular numbers, because if you plot them using little blobs like this, you get this triangular shape, 5, 4, 3, 2, 1. Now, there's a lovely geometric property of triangular numbers, which is if we take a copy and we flip it around, it's always going to make a rectangle, and that rectangle is always going to be however many elements we had, it's going to be that many elements high, and it's going to be that many elements plus 1 across the bottom. And because we only care about the blue squares, if we know how many things are in the list, we know how many comparison operations we are going to need to do. We are going to need n as the number of things in the list, multiply that by n plus 1, and then divide the whole lot by half. Now, this is where the big O notation gets a little bit weird, because big O basically says when these numbers get big, which ones are still going to matter? N times n plus 1 all over 2. Well, first of all, that n over n times n plus 1 becomes n squared plus n, because we got n times n and we got 1 times n. And the over 2, now big O says, well, the over 2 doesn't matter, because the 2 is not going to get any bigger, so we can just ignore it, get rid of that. Now, as n gets bigger, if we get to like n is 10, now n squared is 100 versus 10. If it's 100, now we've got 10,000 versus 100. If n is 1,000, now we've got 1,000,000 on that side, we've got 1,000 on that side. As the number gets bigger, the n becomes insignificant, so we just throw it away. We're like, we don't care about that. That's not going to be the big deal. The big deal is the n squared. That's the number on the left. And so this deduplication of a non-sorted list, this is big order n squared. Now, the way that this plays out in reality, let's say that you've got a social media platform where someone chooses their username, and you need to check, is that username already taken? And because you vibe coded the whole thing, you've got all that data in a database that isn't in order and it doesn't have any kind of search key on it. If you have 100 users, it's taken 100 milliseconds to say, yes, that username is currently available. What is going to happen, though, is you get 200 customers, now it takes 400 milliseconds. At 800 customers, it's going to take 6 seconds to tell you that your username is available or unavailable. If your company doubles again overnight, now 25 seconds. If you double again, it takes 2 minutes. If you get to 10,000 users, it's going to take 27 hours to tell you whether your username is available or not, because the data is not sorted. If the data is out of order, then this is how the algorithm performs. You get a little bit bigger, you get a hell of a lot slower. If your data is in order, then it's almost linear, because it's always, if your data gets twice as big, it only takes 1 step to cut the thing in half and look at the half you're interested in. Now, there is another, this is the kind of the value, this is the reason why sorting data is such a big deal, and a lot of the algorithms we're going to look at, they rely on a sort of, they break things down into smaller parts and then they reconcile them, and they do it based on the fact that if you have 2 lists which are already in order, it is relatively quick to combine those into one big list which is in order, because all you do is you keep looking at them and going, that one, 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 and you just take the one at either side and you splice those into the, like, riffling 2 subsorted decks of cards. It's known as a merge sort. And the merge sort algorithm basically takes your deck of cards and it breaks it in half, and then it breaks the halves in half, and then it breaks the halves in half, and it keeps going until each pile's only got 1 card in it. And then it puts the piles back together by going to the small one and then the big one. And then it takes those 2 piles, like small one, small one, small one, big one. And it runs like this. Now let's look at a couple of other examples. There's a thing called the insertion sort. The reason insertion sort is interesting is that once it's sorted, if you have new data being added to the set, the cost of adding that is very, very small. So the initial sort takes a little while, but then when a new customer comes along and signs up, it's very easy to figure out where to put them. Insertion sort runs like this. That's the point where someone definitely comes in and says, I knew it, you're playing Space Invaders in here. Look at the cocktail sort. Cocktail sort is bubble sort, but it goes in both directions, like a cocktail shaker. By the way, all the algorithms here, I've translated them all so they play in F sharp minor, which is why they all sound like a little bit friendly. Shell sort is one of 2 algorithms here named after a person. Shell has nothing to do with like the Bourne shell or the Bash shell or PowerShell. It's nothing to do with C shells. It's invented and named after a guy called Donald Shell, who created it in 1956 when some colleagues said, yeah, we're going to use this. And he looked at it and went, I think I've got a better idea. And shell sort looks like this. And there's Tim sort, which was invented by Tim. Tim Peters, 2002, was the person who built the sorting algorithms that became part of the Python programming language. And I don't know why they decided to name it after his first name, because that's not normally how we do stuff in science. But this is Tim sort. And yeah, Tim sort, if you sort anything in Python, And then finally, there is the one which has become the de facto, because pretty much the best one we've ever found. General purpose sorting algorithm for randomly distributed data is an algorithm called quicksort. Now, where this gets really interesting, let's make them race. So this is all of those algorithms applied to a stable, so they've all got the same input here. You can see the initial state of all the data on there is the same, and we're going to run them starting at the same point, running at the same time. I've only got sound effects for one of them, otherwise this would be cacophony. But you can see here, quick sort's done, Tim sort's done, shell sort's done, heap sort's done, insertion sort is done, bubble sort is still there in the corner eating glue, going, come on, you can do it, and there we go. Now, this is why these different algorithms matter, is because they have different behavior. Quicksort is normally best. If you're working with .NET, the built-in, if you have a list in .NET and you say just sort this list and you give it a comparison function, the built-in library is smart enough to check if your list is one of the degenerate edge cases that is going to make quicksort slow, and it will use an insertion sort instead. So this is what I mean about don't roll your own, is the people who do this at a language level, they've put in all kinds of optimizations and things that I'm sure you'd eventually figure out. But you'd only figure them out after you'd taken the website down a couple of times and customers shouted at you, and you're like, why? It was working yesterday, but every time this one customer tries to sign up, it takes 27 minutes to check their password. So the built-in optimizations that you get in a lot of languages, they got some really, really clever stuff. They know about the degenerate cases and the edge cases. Now, there is one more. I said I was going to try not to have any actual code in this talk, but this one, Rendell sent me this, and it's just too good not to include. This is known as the timeout sort. And this is implemented in JavaScript. And what we're going to do, we're going to have a list of numbers. And then we're going to say, all right, for each item in the list, I want you to do window.setTimeout. And it's going to take the item and it's going to print it after that many milliseconds. There we go. Idiot sort. Now, it works. But you don't know how long it's going to take, because if there's something big on the list, like if you've got a couple of million in there, it's going to take millions of seconds to run. But I thought the top number there, by the way, the 100073, that's not a number. That is the numeric handle of the timeout function, because JavaScript is an entirely logical language. That is O of n. Yes, it is, depending how big n is. Yeah. So that's, it's in time based on not the size of the data set, it's in time based on the biggest thing in the data set. So we need a tiny banana to get the big O for that one, right? So we've looked at a bunch of things for how to take data, put it in a dictionary, sort the dictionary, and tell, is the thing we're looking for, is it in the dictionary or not? But actually, the reason why things like spell checkers are useful isn't just they say, hey, you made a mistake, because you say, this is a slide from my talk about algorithms. I'm going to present it at a conference next week. And PowerPoint goes, ha, 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 human, you're an idiot. That's not a word, which is not terribly helpful. What I want is useful suggestions about what word might have been supposed to go there. Now, we are not getting into things like statistical language models. That is a whole other way of processing natural language. What we are looking at here is deterministic spell check, deterministic algorithms, and the thing underlying most spell check systems is something called the Levenshtein distance. And Levenshtein, go on Wikipedia, you're like, so Vladimir Levenshtein invented this in the Soviet Union in 1965, and Wikipedia says that the Levenshtein distance between two strings, A, B of length A and B modulo A and modulo B respectively, no. I mean, if you can read maths, knock yourself out. Most of us are like, no, what does it actually mean? Well, Levenshtein distance tells you how far away this is from another word. How many edits do you need to make? So if we take the word coference, and let's say we want to measure the Levenshtein distance between coference and coherence. So the C, we don't need to change that. That one's fine. The O, we don't need to change that. That one's fine. The letter F there. Now, if we, we'll do coherence next. We'll do coffee. Maybe I meant to say coffee. So C-O-F-E. That one we need to delete. We can keep the E. The N we need to delete. The C we need to delete. And the E we get to keep. So to get from coference to coffee, 1, 2, 3, 4 edits. That's the Levenshtein distance from that word to that word. Let's look at another one. If we are looking for the word coherence, which is also a dictionary word, the F has to be edited, replaced with an H, but the rest of them just drop straight in. So this is a pretty good candidate. This is only one edit away from a word that's actually in the dictionary, so maybe that's what I meant to say. If we look at the word conference, now the N here, that's an insertion, but the rest stay where they are. So also Levenshtein distance of 1. We only need to make one edit to get from coference to conference. And just to kind of demonstrate a degenerate case, if we said, well, what's the difference between coference and marmalade? Well, we can keep the E, but all the rest need to be changed. So the distance between coference and marmalade is 8. And so what spell checkers do is they crunch the thing you typed that's not in the dictionary against everything in the dictionary, sort it by the Levenshtein distance, and pop up a little window that says, well, which one of these did you mean? We found, and we're like, yeah, conference. Actually, that's the one that we wanted. So we're doing great. Like, you know, we've started off with talking about the basics of algorithms, where the word came from and how Facebook isn't one. And we've invented dictionaries. We've invented spell checking. We've come up with various sorting algorithms. We've done bubble sort. We've had a little bit of authentic Viking helmet demonstration on stage. I think we've probably earned a pint. So we're going to go to the pub. Now, we're not just going to go to any pub. We are going to go to the historic town of Aylesford, which is a place very close to my heart for several reasons. One, it doesn't actually exist. 2, there are no roads in or out of the historic town of Aylesford. And 3, the town of Aylesford has a pub on every street corner. Now, the problem that we have is we want to know if we're having a beer at the Anchor at the top there, and we get a text from someone going, hey, come and join us, we're in the Hatchet. We want to know the best way to get there. We want to know the most efficient route. Now, fortunately, we've got a map of Aylesford, which has these indications on it. What we need to do is we need to figure out what's the best way to get from the Anchor to the Hatchet based on the walking times in minutes that are on our map here. So let's meet Dijkstra's pub crawl algorithm. Now, this is how this one works. We're going to go to the Anchor. We always start at the Anchor. It's the best place to start a night out. Then we are going to find the nearest pub that still has beer. We're going to designate that P. We're going to go to P, and then we are going to go to every adjoining pub to see how far it is. And we're going to check the distance. We're going to have a pint at each one of those. Then we're going to go back to P. Now, if we found a shortcut, we are going to update our little score sheet of how far all the pubs are. When we've been to every adjoining pub, we're going to go back to P, and we're going to drink all of their beer. And we're going to keep doing this until we've drunk all the beer in town. The universal algorithm. Are we done? No, there is still beer in Aylesford. We're not done. All right, what's the next step? Find the nearest pub, go to all the neighboring ones, have a pint, go back, drink all their beer, go back to the Anchor, keep going until we've drunk all the beer in town. So we're going to start here. We'll start at the Anchor. Now, this is our score sheet. Initially, the distance to the Anchor is 0. The distance to all of the other pubs is infinity, as far as we know. And the Anchor, to get to the Anchor, we don't go via anywhere. We just start there. So let's go to the Anchor. There we go. So what's the next step? We'll find the nearest pub that still has beer. Well, we got our little map. It's the Beehive, the Crown, or the Duke. It's going to be the Crown. So that's the Beehive. We're going to go to the nearest adjoining pub. The Anchor here is the nearest pub that still has beer because we're already there, so there's no distance. So we'll go to the Beehive. We'll have a pint. We'll update our chart. The Beehive's 15 minutes away if you're starting from the Anchor. We're going to go to the Crown, have a pint. The Crown is 8 minutes away if you start at the Anchor. We're going to go to the Duke. The Duke is 18 minutes away if you start from the Anchor. Go back to the Anchor, drink all their beer. Right. Is there beer left in town? Yes. Okay, so what does the algorithm say? Go to the Anchor. Well, that's cool. We're already there. Find the nearest pub that still has beer. Which one is that? Based on our chart here, we got a 15 and 8. So it's the Crown. The Crown is an 8-minute walk. We know they still have beer. So let's go to the Crown. And then we go to every adjoining pub. So let's go to, mark that as P. We're going to go to the Eagle. The Eagle is 20 minutes away if you get there via the Crown, which means it's 28 minutes from the Anchor. We'll update that one. We'll go to the Duke. The Duke is 18 minutes away. Now, at this point, we've already got to the Duke in 18 minutes, but now if we go via the Crown, it's 8 plus 7, which means we found a shortcut. So we take that, it's not 18, it's 15. It's actually quicker if you have a beer on the way. That's why Dijkstra's algorithm is so important. We're going to go back to the Crown, and we're going to drink all their beer. The Crown is now done. Is there beer left in town? Yes, so we go back to the Anchor. Right, what's the nearest pub that still has beer? Well, the Anchor's dry, the Crown is dry, the Beehive and the Duke, they're both 15 minutes away, so we're going to pick one. So let's go, yeah, you know what, we'll go to the Beehive. And then from there, the beehive is now P. We're going to go to the griffin, and we're going to have a pint, and we're going to update our chart. The griffin is 34 minutes away if you go via the beehive. Then we're going to go to the eagle. We're going to update now. At this point, that's where it gets interesting. Only update the distance if you found a shortcut. We've already managed to get to the eagle in 28 minutes. If we go to the eagle via the beehive, it takes longer, so we don't update it. It's not a shortcut. We haven't found a shorter distance. Back to the beehive, drink all of their beer. What's next? Back to the anchor. Next pub that still has beer, that's the Duke. So we'll go to the Duke. That's P. We'll go to the Fox. We'll have a pint. We'll update the chart. We'll go to the eagle. Whoop. Why didn't we go? Oh, no, we didn't go to the eagle because we've got to go past a pub to get there, and that's not the rules. We'll go there in a minute. Back to the anchor. What's next? The Fox. All right, the Fox is now P. We'll go to the eagle. Have a pint. Update our chart. Go to the inkwell. I missed a step in the animation. All right, so the eagle is P. We'll go to the griffin. We'll go to the hatchet. We'll go to the inkwell. Update our chart on all those. Back to the eagle. Drink all their beer. Back to the anchor. What's the closest pub that still has any beer? We're looking at our chart here. It's probably going to be the griffin. So we'll go to the griffin. That's P. Go to the hatchet. Drink all their beer. Back to the anchor. What do we got left? Well, the hatchet and the inkwell. Okay. Inkwell's looking a little closer. That's P. Go to the hatchet. Update the chart if we need to. Back to the inkwell. Drink all of their beer. Go back to the anchor. What's the closest pub that still has beer left? Well, it's got to be the hatchet. It's the only beer left in town. So I'm going to go there. Can't go to any neighboring pubs. We've drunk them all dry. So update the hatchet. That's our distance there. Boom. Done. We've drunk all the beer in town. And we now have an accurate distance table of how to get from the anchor to any other pub in Aylesford. But to find the optimum route now, what we do is we take that table we've constructed and we work it backwards. So if someone says, yeah, come and meet us, we're having a beer at the hatchet. We sit in the anchor, we look at the thing, we figure out we're going to finish our drinks. Okay, so the hatchet is 45 minutes away, but we get there via the inkwell. All right, well, how do we get to the inkwell? Well, we get to the inkwell via the eagle. And then we get to the eagle via the fox, and then we'll get to the fox going via the Duke. We get to the Duke by going via the crown, and we get to the crown directly from the anchor. So this is our shortest path. This is what Dijkstra's algorithm does, is apart from letting you drink a lot of beer in a lot of pubs, it allows you to find the shortest distance between a bunch of nodes in a graph where you know the distances or the weights on the lines that connect all of those things. Now, most of the pubs here are made up, but 2 of them are real. Because the hatchet is an actual pub. The hatchet is in Bristol in the west of England, and the anchor is in Stockholm, Pub Anchor, and they are both excellent rock and heavy metal pubs, and they are great fun. So if we really did want to go on a pub crawl from the anchor to the hatchet, or from the pub anchor to the hatchet, if we go onto Google Maps and we say, I want to go from here to here, it's using the same algorithm. Now, Google Maps is not smart enough to go from pub to pub to pub to pub. What it does is it navigates the junctions between street corners, but the set of walking or driving or public transport directions that you get out of things like Google and Apple Maps, that's applying the same algorithm based on taking the edges of a graph that tells you how long it takes to get from here to there and there to there, working all the way down, and then tracking it backwards so you know where to start from with each part. Now, I want to finish up by going back to this idea of algorithms being the nuts and bolts of software development. They're important. We should understand them. We should know how they work. We should know how to choose the right one to solve a particular problem or do a particular piece of work. But most of the time, they're not something we really think about very much. You choose the right one, you plug it in, you get on with your job, or you get on with whatever you're trying to do. But there is a wonderful, wonderful book. It's by Robert M. Pirsig. It's called Zen and the Art of Motorcycle Maintenance. And now my favorite thing about this book is when Pirsig wrote it in the 1970s. It's a story of him and his son taking a road trip across the United States on motorcycles. And all these meditations about kind of thinking about Zen philosophy from the perspective of what it's like maintaining the bike that you're using on your road trip. And when he wrote it, it was kind of semi-autobiographical, so part of it was nonfiction and part of it was just meditation. And along the way, he invented something that turned out to be some quite good philosophy. And so when they had to put the book on shelves in bookshops, they're like, well, it wasn't supposed to be a philosophy book, but we think he invented real philosophy in it, so maybe we'd better... And so now, if you want to go and look for it used to be in, like, travel, and eventually it moved across into the philosophy section. Pirsig is now credited with creating something called the metaphysic of quality. That does not matter for the purpose of enjoying the book. The book has this lovely prelude that says, please don't take this as authoritative about Zen Buddhism. It's not much good about motorcycles either. But there's a passage in this book which stuck with me as much as anything that I have ever read, where he's talking about doing some maintenance on a bike, and there is a stuck valve inside the engine on the bike, which is not a big deal. And all you got to do it is you've got to remove the one side of the engine cover, take the thing off, so you undo a couple of screws, take it off, free up the valve, and you're good to go. And then one of the screws won't come out. He's got this bike, he's got this little screw, like a screw that costs 5 cents in a hardware store, and the screw is stuck. Now, if you've ever had this experience doing your own mechanical maintenance, you're like, I got to change a tire on my bike. Okay, changing a tire on your bike is easy, but then you got to try and remove the wheel, and the thread rounds off on the thing, and now the spanner won't bite, and you're like, this was supposed to be an easy job, and now it's a hard job. Now I don't even know if it's possible, because something that I thought was too simple to go wrong has gone wrong. As Persig says, normally screws are so cheap and so small that you think of them as unimportant. But now you realize that this one individual particular screw is neither cheap nor small nor unimportant. Right now, this screw is worth exactly the selling price of the whole motorcycle, because the motorcycle is valueless until you get the screw out. With this re-evaluation of the screw comes a willingness to expand your knowledge of it. And I think of algorithms like that. Most of the time, you don't have to worry about them. But just a handful of times in my own career, there's been something like a search form on the internet that just for a particular customer, it didn't come back. Like it was taking 35 seconds if you searched for a particular customer or a particular email. And it's those moments where you're like, well, it should be simple. It should be, cheap and small and simple and not important. But maybe now is the time we need to figure out how this thing actually works, because right now our entire website sucks because of something we thought was too simple to possibly go wrong. And with that realization comes a willingness to expand your knowledge of it. Folks, any questions? The silence of complete enlightenment. I teach here. This is my university. Welcome. I do have certificates, but they are self-adhesive, and they say Rockstar Developer on them. So. Folks, I will be around at the party this evening. I will be around the conference tomorrow. By all means, come over, say hello, chat to me about any of the stuff in the talk or any of the other things that I do with code and music and video and algorithms and CSS and all that kind of stuff. Have a fantastic time. Enjoy the rest of the conference. Thank you for coming.